that will be how we proceed. All right. Oh, additionally, most of what we will go through is also included in your printed notes. All right. So we should be able to go through with some amount of efficiency. So we have before us, well, it says a square wave, but as was pointed out in the lecture, this is really a rectangular waveform. The square wave would have been equal above and below the time axis. But be that as it may, what we're interested in identifying, we spoke about the periodic time taken to complete one complete cycle of the waveform. We looked at the square wave. We also looked at the triangular wave. Again, noting the time period, time taken to complete one oscillation. We referred to these waveforms as periodic, simply meaning that the same waves were repeated at a given time interval. That time interval represented by the periodic time that we just mentioned, big T. And if we were to represent that mathematically, right, then what we're saying is that f of t is equal to f of t plus t. And this mathematical representation, all it means is that the waveform f of t after a time t, periodic time, is repeated. All right, that's all this expression refers to. T, of course, as we mentioned before, is the periodic time, right? And the frequency of the waveform would be equal to 1 over t. So the reciprocal of your periodic time will give you the frequency of the wave. Now, I jumped straight into talking about the square wave and the rectangular waves, but when would we ever encounter these? The bottom line is, in electrical engineering, you're going to encounter waveforms which are non-sinusoidal. So if it makes it a bit more palatable to you by referring to the waveforms as non-sinusoidal, then fine. And I highlight that because all the analyses that we have done so far on AC circuits, when we looked at resonance, all the analysis that we have done assumes, or not really assume, but all the analysis that we have done is based on sinusoids, okay? So we have all the AC circuits we looked at, we were dealing with sinusoids. What we are now going forward to looking at on the complex waves are that there are other waveforms to consider. There are other voltage signals to consider. Signals which may be square, signals that may be rectangular, and how do we treat with these, all right? So that's the real purpose of looking at complex waves. We also need to talk about aperiodic waves, or waves that are non-repetitive. Based on what we have here, the question is, where does the wave start, where does it end? If we are using the crossing of the zero axis meaning the time axis, then it is obvious that that wave will be different from that wave, all right? Which makes it aperiodic or non-repetitive, okay? So those were all addressed in the video presentation. Now, having spoken about the fact that we have dealt with sinusoids, we look at the whole process of frequency synthesis, which is, if we were to add some waves, add some sine waves, how would those look? Or what could we achieve by adding these waves? And we showed that by adding these sinusoids, we were able to create something that was heading towards becoming a square wave. In this instance, we're adding waveforms with frequencies that were odd multiples of the frequency of the square wave. And we saw that these, when added, were getting closer and closer to being a square wave. If I just look at the third one, right? So in adding these four waveforms, so we now have 100 sine omega t, 40 sine 3 omega t, 20 sine 5 omega t, and the 7 omega t. When we add them, we saw that the top portion of our waveform, yes? I mean, obviously it's not complete, but we saw that it was getting flatter and flatter. If we look at the previous slide, all right, oh, come on. Again, it's not very obvious, yeah, but the fact is it's getting flatter. Let's take it from me that it is getting flatter. And what we are saying is that the more of these waveforms, the more of these sine waves that we add, these sine waves, the more of them that we add, we would ultimately see a square wave, which is gonna look like that, all right? So ultimately that is what we will see. Now we speak here of frequency synthesis. I have told you that we are adding these waveforms whose frequencies are odd multiples. Now, the question is, how did we determine that these were the waveforms that we needed to add? And the reverse of what we're defining here as frequency synthesis is harmonic analysis. So what you will do, or what you have done, depending on whether or not you have already covered it in mathematics, is that you would do the harmonic analysis using what we refer to as Fourier series. So in completing your Fourier analysis, you're determining the component sine waves that will make up these complex waves. So the synthesis, I just showed you that we added these waves to get the square wave. The analysis is that we would have had the square wave, or we would have sought to determine which sinusoids are part of the complex wave. All right. And so that harmonic analysis, when done, will produce these sine waves. And these sine waves, we give them, you know, we apply a certain nomenclature to them. One is that we have one of the waves, which we refer to as the fundamental. It has the same frequency as the waveform that we're analyzing. So if we're analyzing a square wave with frequency 50 Hertz, having done the analysis, we will get one wave, which will have a frequency of 50 Hertz. And that sinusoid is known as the fundamental. All right, so our fundamental is that large wave. There are other waves that are in existence, and these waves, remember I just showed you those that had odd number multiples. In this instance, and just speaking generally, these waves have frequencies that are exact multiples. So for the square wave, we had odd multiples. But the general statement we are making is that there are now some other waves in addition to the fundamental, which have frequencies which are multiples of the fundamental frequency. And these waves we refer to as harmonics. All right? And then we refer to these harmonics ordinally. All right? So for the harmonics, we have, well, for our complex wave, we therefore have the fundamental, which is that big wave, which has the same frequency as the original wave that we are analyzing. But then we have the harmonics. And so you have the third harmonic, you have the fifth harmonic, you have the seventh, Of course, if we continue to have the 9th, the 11th, the 13th, but these are the harmonics that are part of a square wave. If I went to another wave, I may not have any odd harmonics. I might have only even harmonics. And then there may be a third wave that we analyze that will have all the harmonics present. So you may have second, third, fourth, all the way up to infinity. All right? So we make the distinction between fundamental and harmonics. In terms of the math behind Fourier analysis, Fourier series, or Fourier analysis, that is the expression that we would need to complete. All right. So the function is given by a0 over 2 plus from n equal 1 to infinity, what we have there in the bracket. And then we would now need to determine the coefficients a, b, a0, b, a0, an, and bn. And in finding those, we would use these expressions. No, it's not necessary for you to write these to know them. All right? We are not focusing on the math of harmonic analysis. What we are focused on is the application. So I'm not asking you to do the Fourier series. When you get to math, you will do that. All right? So I have to assume that you will be able to do that. What we're going to be focusing on is how to apply them. All right? So for the square wave, and we have been saying it quite a bit, the square wave, that's the expression. If I had a sawtooth, that would be the expression. And based on what we just said, for the sawtooth, you're seeing that we have here all the harmonics. So we have the second, we have the third, we have the fourth, we have the fifth. That's for the sawtooth. For the square wave, however, we have the third, the fifth, and the seventh. So we only have the odd for the square, but we have all for the sawtooth. All right? And as I said, you may go to another waveform, and all you will have would be the even. And so the harmonics are going to be dependent on the waveform that we're analyzing. Additionally, there may be a waveform in which the fundamental is not represented. All right? And so all you would have are harmonics plus a non-sinusoidal component. And that, let's go back to the equation. If you note, there's that component a0 over 2. Now, a0 over 2 obviously does not have a sine or cos attached to it. So it means that it would not be cyclical. All right, so that's a constant. Now, if you're thinking of a voltage as a constant, what would that represent? If it's constant, what would it represent? Anybody?
DC. DC, sir.
DC. All right. So it means that in your Fourier series, that constant component would be the DC component. All right. Okay. Next, all the circuits we have dealt with, all the AC circuits we have dealt with, we have spoken about using the RMS value. And we made it abundantly clear, and we stated that if, unless otherwise specified, you must assume that the voltage given in a circuit, in an AC circuit, is the RMS value. But what is the RMS? I mean, yes, we know it means root mean square, but how do we define RMS? All right. Now, the RMS value is simply the value of the AC, which produces the same heating effect as its equivalent DC. All right. So if I give you an AC voltage, yes, we are saying that the root mean square of that AC would be the voltage which is equivalent or which produces the same heating effect as its equivalent DC. All right. So when I'm dealing now with my complex wave, I also have to treat with the RMS value. So I need to use the RMS of the complex wave. Now, because you have been using, or we have been applying, or let me not say applying, but we have been using, or we have now grown accustomed to analyzing circuits with sinusoids. When we come to complex waves, all we are going to do is a repeated application of what we already know. We'll come to that in a little more detail, but just focusing a little on the RMS value. We use here the superposition theorem to explain RMS. And here we are assuming that each of these sources would represent the fundamental. For E2, that would represent the second harmonic, yes? And for E3, that would represent the third harmonic. Fair enough? So those are the harmonics and the fundamental that is in the wave. And by applying superposition, we know that the power dissipated in the resistor would be E squared over R. And so E in this expression would be the RMS, and E1, 2, and 3, yes, are from the three sources. Good. Now, I want to make a distinction quickly, and that is E1, E2, and E3 are RMS values. All right. However, I'm distinguishing this from E1M, E2M, and E3M. With the M, what these represent are the amplitudes of the waveform. So if I were to write the instantaneous value for E1, E1 would be equal to E1M sine omega t, where omega here would represent the angular frequency, E1M, the amplitude, and the fact that I'm using lowercase e, it means that it is the instantaneous value. And that is the instantaneous value, or the value at the time t. All right, good. Not seeing anybody writing, so that means that is good. That is clear. Okay. So from that, using well, we come to find that the RMS value in terms of the voltage is given by the sum of the squares of the individual RMS values. And this is true not only for the voltage, but it is true for the current. All right? So the RMS for the voltage, the sum of the squares of the individual RMS values, and this is true also for the current. All right, I pause briefly. Any questions? Okay, all right, so continuing. We have a full wave rectified wave. It has an amplitude of 30 and pre-rectified frequency of 60 Hertz. We're asked to calculate the DC component and the RMS values of the harmonic components up to the sixth. And we also are asked to determine the harmonic frequencies. Okay, I know the question is already completed in your lecture notes, but you know, for what it's worth, we'll just go through it quickly. All right. All right. Now, for the full wave rectifier, the expression is that E is equal to 4EM over pi into a half plus cos 2 omega t, that's over 3, minus cos 4 omega t over 15 plus cos 6 omega t over 35. All right, so that's the expression, that's the Fourier expression, and of course, plus, and we continue to infinity. This is the Fourier expression for your full wave rectified wave. All right, and remember what your full wave looks like, something like that. So obviously, this waveform is not sinusoidal. All right, it's not sinusoidal, so it is a complex wave. So it means that from your in fifth form and looking at rectification, that you were dealing with complex waves. That's just the reality. Now we're at the point where we have to think about it. We have to do the analysis with the complex waves. And the bottom line is, when you were, again, I go back to high school, when you're in high school, having gotten that output, when you put in your 4 diodes or your 2 diodes, yeah? Having gotten that output and you wanted to now get pure DC, which was just a straight line, your teacher may have just told you, okay, we put a capacitor here, you put an inductor there, or maybe you used an RC, okay? Or just the capacitor, and you got a better DC output. Question is, what value capacitor did you select? Or what value inductor did you select? And why did you put the capacitor in parallel, and why did you put the inductor in series? By knowing what the component sine waves are, in this case, and of course, cos and sine, well, cos is simply sine shifted by 90, right? But knowing these harmonics, you are now able to accurately determine what value of capacitance or what value of inductance you're going to put in. And you know, based on your understanding of theory, you'd know, well, this is what capacitors do, this is what inductors do. And seeing that this is the most dominant harmonic, you're then able to make a determination as to which one you need to get rid of to get your pure DC. Yes, Ms. Alexander.
Sir, I have a question. So the equation that you have on the screen just now, is that something that would be given, or we'd have to deduce that?
I said earlier that I'm not requiring you to do the derivation, just to apply. So yes, you would get the necessary equation.
Okay.
All right, good. All right, so we have the expression here. And we're asked first to find the DC component. All right. So what would be the DC component?
The 4EM over pi times half.
Yes?
The constant part, sir.
Which is?
4EM over pi times half.
Okay, so that's before EM over 2 pi. All right. Everybody comfortable with that? All right, good.
Sir, excuse me, sir. So how you get the half, sir?
How I get it?
Yeah.
Brandon, tell him.
Oh, they're not the equation, and because it doesn't have a cos or sine part, that means it don't oscillate.
All right. Thank you, sir. All right, thank you, Brandon.
But no, man, I me answer, man. But him answer through me, but I understand you.
All right, sir. All right, sir. Thank you, sir.
All right, next. We were then asked for the RMS values of the harmonic components. So it's just the components we are interested in. All right. Now, question. Do we have the fundamental represented in this equation? Is the fundamental represented in this equation? Come on, man, we can't have such long
No, sir.
silence here. No, why?
No,
Why is
sir.
it? Why do you say no?
Because from the equation it starts at cos 2 the omega t.
And 2 omega t would represent what?
Second
harmonic.
harmonic.
Beautiful.
Second harmonic.
Beautiful. All right. So we, for the second harmonic, yes, for the second harmonic, what would be the peak value? Mr. Bernard, let me see if you really understood what Mr. Denham said. What's the amplitude for the second harmonic?
Right. Sir, we're not sure I know, sir.
Which means that you didn't understand what he said then.
Sir.
Then why you tell him thanks?
All right, sir. This is the reason we have the half, sir. Can you give us the equation, right? And this is
No. I gave you the equation for the Fourier expression for the full wave rectified wave. So this entire expression that is written on the screen is for the wave. The half is a part of the expression.
Okay.
Good. So it's the second time you're saying okay. So if it is really okay, I am now asking you, what is the coefficient, or what is the amplitude rather, of the second harmonic? Come on, just tell us something, and then we know what we need to correct. What is the amplitude?
Sir, I'm not sure, sir.
What we mean by amplitude, Mr. Bernard?
Sir, all right, from 0 to the highest point, our lowest point.
And when you write a sinusoid, what of the sinusoid would represent the amplitude?
So the part in front of the cos part, them, sir, like.
Yeah, so what is in front of the cos?
Oh, 1.
You
right?
see 1 there, Mr. Bernard?
Sir, but that normally if
Do you see 1 in front of cos 2 omega t?
Yes, sir. I believe it's there. Because anything multiplied by at the same thing, sir.
Somebody rescue me now, please. Anybody, rescue me. Rescue me from the hands of Mr. Bernard.
1 over 3. Equation be multiplied by 1 over 3. I think
it's 1 over 3, but that's incomplete, Mr. Alston.
And then you go times it by the constant. The 4e over constant.
Okay, so give me now, Mr. Gibbs.
So 4 EM over 2 pi times.
What you get 2 pi?
Over pi, sorry.
But Mr. Gibbs, you were telling me the right thing now that me focus on you start telling me gypsy.
Over pi, sir, times 1 over 3.
Okay, so what is it, Mr.? Give me the complete thing, man. I'm not writing so much. 4 EM over?
Over pi, oh. Over 3 pi.
Okay. Network's not hard, you know. Scary, yes, but not hard. Anyway, and what is EM?
So is it
What is
EM now?
EM? Yes, Mr. Bernard?
The amplitude, sir.
What? Mr. Bernard, just right.
All right.
That's right. What is EM?
30, sir, 30.
30. You're giving it in the problem. So it is 4 times 30 over 3 pi. Yes? So that gives us 40 over pi. Now that is EM. So that will be E2M, meaning this is now the amplitude, yes, of the second harmonic. But what were we asked for? RMS values of the harmonic components. So if that is the amplitude, how do we find RMS? And what's the relationship between amplitude and RMS, Mr. Bernard? I was joking about
Not you taught me to write, sir. I'm just right.
Yeah, man. I know you were going to jump on that one, but tell me, what's the relationship between amplitude and RMS?
Sir, let's see.
How do we find RMS?
So now the E square root E1.
No. What is the relationship between the RMS value of an AC and its amplitude, its peak? Forget about what we are teaching this morning. What is the relationship between the RMS value and peak? How do we find RMS from peak value?
So some more root 2, some.
All right. So it's E2M over root 2, all right? So it's 0.707 times peak. So the E2 would therefore be equal to 40 over root 2 times pi. All right? Okay. Now, any questions? Remember what we're asked for, it's just the RMS of the harmonic components. It's not the RMS of the waveform, just the RMS of each component. So, given this and the fact that I'm hearing no questions, let's see now. So Henry, Javoy, what is the peak for the fourth harmonic?
Peak 4 over 4 EM over pi 4 EM pi over times 1 over 3.
I'm giving you one more chance, hurry up.
All right. So I said the peak.
The peak value for the fourth harmonic.
Is that you have the coefficient of the cos 6 omega t over 35.
You reach a 6, Mr. Henry.
Out of
all right.
1 over 15. 1 over 15. 4 EM pi times 1 over 15.
Just tell me the exact thing to write. I'm not multiplying anything. Just tell me the final thing.
4 EM over 15 pi.
And what is EM?
30.
So that's 8 over pi, right?
Yes, sir.
Good. All right. Now, I know that we have a minus sign there, and if you included it, I'm not going to, worry too much about it. One thing you will realize is that the minus will not impact your final solution. What the minus does really is you would have to repeat the expression for the current with the plus and minus. Right? This is just how we put the curves together, but in terms of calculating the RMS values, the minus will not impact that solution. And you'll see it in a few. So if that is the peak, so Harrison, what's the RMS? If the peak is 8 over pi, what's the RMS? Alex?
Yes, sir. So the RMS would be, sir, E4M over.
No, man, we finished that already. Here's the peak. So I'm saying, what's the RMS? Are you seeing the screen?
Yes, sir, I'm seeing the screen, sir.
So I'm saying the peak is 8 over pi. What is the RMS?
I'm not sure, sir.
So I want you to all explain something to me. When I went through the process for E2, I wrote it down, and then I asked a simple question. I paused and asked whether or not it was clear. I got no feedback. 3 minutes later, I'm asking the same question. Are you telling me you're not sure? So is it that you didn't understand what we did here? Is that what you're saying to me, Mr. Harrison? Yes or no, Did you understand it?
Not fully, sir.
So why, when I asked if you had any questions, you kept silent?
I was just trying to process it, sir. Probably just need a little more time, sir.
Oh, I see. I see. All right. So E4M would have, again, be peak over root 2. So it's just 8 over root 2 times pi. You can figure out this one. But, students, your lack of understanding and you're saying that you're not following tells me two things. You want to know the first one? The first one is that you did not watch the video. You want to know the second one? The second one is that you have not read the notes, because every single thing I'm doing right now is written in black and white and fully calculated in the notes. Now, if it's in the notes, I would say read, we say watch the video, and you come back to me this morning, tell me, boy, it's the first you're seeing it and you're processing it. On what basis can I really teach you and get you to succeed? The unfortunate thing with a module like this, well, I don't know if it exists with other modules, but you won't learn it by osmosis. It can't happen. You have to do the work. You will not succeed on a hope and a prayer. You have to do the work. The other aspects ask us to calculate the frequencies of the harmonics, but as I said, it's already in the notes, so I'm not gonna spend any more time on that. I'm gonna move quickly to the latter part of the notes, and here is where I intend to wrap this topic. So we have a voltage source. So this represents my complex voltage. All right, that's the Fourier series for the complex voltage. And we're saying if we connect it across a resistor, So we have it across a purely resistive circuit. All right? Just as if you had an AC and you connect a resistor across the AC. The corresponding current. Again, you know Ohm's law, I equal V over R. All right? The corresponding current, I, is going to be given by that expression. Now, you and I know that current or the resistor will not cause any phase shift or anything like that to occur. So I1M is going to be equal to V1M over the resistance. The resistance is not going to change. I2M is going to be equal to V2M over R. And I3M is going to be equal to V3M over R. So in other words, each of these are going to be divided by R. And that is how you end up with the current expression from the voltage expression. However, if it is that I connected the voltage across a pure inductor, then I'm going to get an expression I1M sine omega t minus pi over 2, because the same principle that you learned with AC circuits is also true here, that the inductor is going to cause a shift, a 90-degree shift between V and I. And so the current is now going to lag the voltage by 90. So each component of the current, the fundamental, the second harmonic, the third harmonic, will all lag by 90 degrees. And it is 90 degrees because we are dealing with an inductor. The other thing I want to point out, that in complex waves, we always use radians. So once you start doing the complex wave question, just switch your calculator to radians. All right. Where, whilst we had V1 over R, V2 over R, V3 M over R, for the inductor, I1M is going to be equal to V1M over XL1. I2M is going to be equal to V2M over XL2. And I3M is going to be equal to V3M over XL3, simply because the inductive reactance, right? The inductive reactance will change based on the individual frequencies. So for the fundamental, I'm gonna get an inductive reactance of XL1. For the second harmonic, I'm gonna get a reactance of XL2. And for the third harmonic, I'm gonna get an inductive reactance of XL3. Similarly, if I was to connect it across a purely capacitive circuit, yes, I1M would be equal to V1M over XC1, I2M equal V2M over XC2, and I3M is equal to V3M over XC3. Again, XC1 to and 3 are the reactances at your fundamental, your second harmonic, and your third. Of course, if we had fourth and fifth, then those would apply. Do you have any questions? All right. Now, that's for a resistor, a pure inductor, a pure capacitor, but that's not life. All right. So you will have where we have the elements combined. If the elements are combined, then we would have, again, I1, Mi2, M, etc., etc. However, what we will not be sure of is the phase angle. So we wouldn't be sure of what phi would be equal to. Neither will we be sure of whether or not it is negative or positive. However, phi 1 would be equal to the inverse tan, yes, of x1 over r. Phi 2 inverse tan of x2 over r. And phi 3 inverse tan of phi of x3 over r, where x is equal to xl minus xc.
Sir, for this section, for the equation, at the top, the last part where it says I3M sine 3 omega t, is it that it is missing the, okay.
All right. Any other question? Thanks for pointing that out, Mr. Alexander. Any other question? All right. So we now get into the business end. All right. So we have the expression V equal to 120 sine omega t plus 20 sine 3 omega t plus 15 sine 5 omega t. Yes. We have it connected across a resistor, or resistance rather, of 10 ohms, inductance of 9.55, and then we have a resistance of 15 and inductance of 19.1. And we want an expression for the current in each instance. All right. So all we want is a current expression. We're not doing RMS yet. We just want the current expression. Okay. All right. So, and I'm going to call on individuals. Mr. Alexander, your hand is still up. Good. So let's start with you.
Sir, that was kind of like
Yeah, man, I know. But, you
a
know,
mistake.
yeah, we just work with a mistake. So what's the first step?
Sir, the first step is to draw the circuit. I
This is
honestly
easy.
didn't finish taking down the question.
All right, go ahead. So the first step is to draw the circuit. All right, so we draw the circuit. And I'm putting in a symbol. Obviously, it's not sinusoidal. We're just showing that it is complex. All right. And we have 10 ohms. V is equal to 120 sine omega. Plus 20 sine 3 omega. Plus 15 sine 5 omega t plus, and we go on. Okay, back to you, Ms. Alexander. So we are connecting it across a pure resistor. What would be the current expression? What would be the equivalent current expression?
The equivalent current expression, it would be IM is equal to VM over R.
Okay, so for the fundamental, what would we have?
For the fundamental, that would be 120.
Yeah, but that's the voltage. We want the current.
120 over 10,
Which is, I can do math in the morning.
12.
Thank you. So it's 12 sine omega t plus
2 sine 3 omega t plus 1.5 sine 5 omega t.
All right, good, and that's it. So that's the current expression. That's part A.
Sir, I think you missed out something of 2 sine. You missed the 3 of omega t.
Thank you. But you know that, Mr. Reid? You know it, all right? Are you from the corporate area, Mr. Reid? Alex?
Sir?
Are you from the corporate area?
Yes, sir. I'm from Spanish Town.
Just around the road, man. Good. The man was saying back in the country, you know, when planting one that it shoot, So now that you have raised your hand, just go ahead with part B.
All right, sir. So for part B,
Hmm.
we draw the circuit again.
All right. So we have our inductor. And we once again have our V. All right.
Excuse me, sir.
Yes.
The frequency was stated.
Uh-huh.
Okay.
Very good question. So if you went in an exam and you buck up on this and you know you need the frequency, what did you do, Mr. Reed? We're not finished with you, Mr. Reed. I don't know why you left the mic already.
Yeah, we know answer, we know.
Oh, all right. So you're going on an exam and you have this, you see this before you, you do have a frequency. What do you do? Talk to me, man. What do you do? You go to the next question.
No, sir, no, sir.
So what do you do? Anybody? What would you do? I'm coming back to you now, Mr. Reed. What would you do? Anybody?
Sir, assume it to be 90.
Assume it to be anything you want. All right? So that's the key. You assume it. So let's take F, because I have already done the question. We're going to take it to be 50 hertz. All right? So now that we know F is 50 hertz, this is how you, and although I still have Mr. Reed on spot, I'm gonna go through the systematic way in which you solve these questions. You have a fundamental and you have the third and the fifth harmonics, yes? So you start by saying, for the fundamental, so for the fundamental, what is XL? Sorry? So we have the fundamental. What is, how we find XL? Knowing that F is 50.
Sir, 2 pi 50 times 9.55.
All right, so 2 pi FL, and that gives us 3 ohms. All right, so you have XL1. So if XL1 is 3, it means that I1M. Go ahead, Mr. Reed. We just wrote it, you know. So if you need to look back at the notes, so you just write, look back at it. So we have I1M would be equal to?
I1M would be equal to 120 divided by 3.
And that gives us 40. All right. Now, for that component, it means that I1 would be equal to 40 sine bracket omega t. And what would be the angle, Mr. Reed?
Minus pi divided by 2.
You realize how networks is, Mr. Reed? Eh? You can't say yes or no. It's only between us. They're not hearing.
Yeah.
No. Easy stuff, this one. All right. And that's for the fundamental. Okay. Thank you, Mr. Reed. You did well.
Yes, sir.
So Miller, you know. Man, start stretch. What is this? So Miller, now that we have dealt with the fundamental, yes?
Yes, sir.
Which harmonic do we have?
Harmonic 3, sir. Third one.
No, third, all right? So we now go to the third harmonic. So the next thing we write is for the third harmonic.
Yes, sir.
We first find XL. So XL3, what would that be equal to?
Would that be 2? So
All right. Work with me now. What do we mean by harmonic? When we say we have a harmonic, what are we talking about? What do we mean by that? So if we say we have the third harmonic, what does that mean in principle?
three times that of the fundamental, sir.
In terms of the frequency. Yes?
sir.
So if I have XL at the fundamental and I triple the frequency, what will happen to XL?
Be 9, sir.
Exactly. You see it easy? So you don't even have to go back to the 2 pi FL anymore.
So, sir.
Because you have tripled the frequency, it means that XL3 is equal to 9.
Yes, sir.
So, Mr. Miller, what is I3M? Just going back to what Mr. Reid said for I1M, look at the expression, what would I3M be equal to? Which is just the amplitude of the third harmonic.
20/9, sir.
But I'm gonna tell us this thing, I just start get easy, man. So I3 now, I hope you're seeing this. I3 would therefore be equal to 20/9 sine 3 omega t minus
pi/2, sir.
I know you don't want to agree publicly, Mr. Miller, but that's not easy.
Yeah, make it so easy, sir.
But that's how it has been sounding from February.
So, sir, the marking, sir, you would accept plus XL equal 9.
That is, of course, if you have already told me that this is true.
So,
you see, I have to make sure. Understand how I mark. I have to make sure that you did not just see the 9 on Mr. Harrison's paper. So I have to understand where you got it from. You with me? So once you have established and shown me that you understand how to find XL1, then you write XL3 equal 3, XL1 equal 9. We're done. We're good. I'm good. Because I know that you know what you're doing.
yes. Understand, sir. Cool.
Somebody had their hand up, but they didn't have a camera on, so I don't know who it is. And they are not in the class. So maybe I should remove them, but anyway. All right. And then we go to the fifth harmonic. So we next step for the fifth harmonic. XL5. Any volunteers? Know that you realize how easy it is?
15 ohms.
Which implies that I5 would be?
Would that be 15/15 sine 5 omega t minus pi/2.
Which means that the complete expression would be equal to I1 plus I3 plus I5. You don't have to write that, I'm just writing it here. So this would be 40 sine omega t minus pi/2 plus 20 over 9 sine 3 omega t minus pi over 2 plus sine 5 omega t minus pi over 2 plus so on. And so that is your current. This would now be the expression for the current. All right, so part C, we now have a resistor. Since everybody now know that we have to draw the circuit first, I'll just go ahead and draw it. We have the resistor. $15, and we have this as 19.1 millihenries. All right, and of course, V is supplying the circuit. Remember, all we are doing is applying what we already know for AC circuits. All right, so part A, we dealt with just resistance. Part B, we had just an inductor. And part C, we now have the inductor and the resistor combined. So, based on the steps that I just went through, what's the first thing we want to do? Volunteer. What's the first thing we are going, having drawn the circuit, first thing, what are we going to know?
So I want to find XL.
That's not the first thing we want to do. What's the first thing I wrote after I drew the circuit? And I said that this is the process. Yes, Mr. Alexander.
Sorry, assume a frequency.
No, man, no, we passed that.
Sir, for the
You're right,
fundamental,
V
sir.
equal 120. That's equal 120.
No, man, no. All right, we have the voltage. We have the voltage. What's the first thing that I did when I said this is the process you go through?
So let's start with the fundamental.
Thank you very much, Mr. Sterling. The first thing we do is to state which of the components we are dealing with. So we start with, for the fundamental. I can't spell anymore, but anyway, you understand. That's fundamental. Figure it out, all right? So at the fundamental, what do I need to determine? What am I determining first at the fundamental? Look back at what you just wrote. What is it that you need to determine?
Excel.
The current.
Yeah, but we determined XL. Why? Why were we determining XL?
To
Because
define
we're
the current.
Based on-
IM.
No, why is it that we were finding XL? Just XL.
Because we're just dealing with an inductor, sir.
Thank you very much, Mr. Harris. We were only dealing with an inductor. Are we only dealing with an inductor now?
No, sir.
No, we have a resistor and an inductor. So what is it that I need to be calculating now?
The
The
impedance.
impedance.
Impedance. So we now need to find Z. So Z1 is going to be equal to R plus XL1. Where XL1, what is XL1?
2 pi FL.
2 pi FL. Again, we the same question, so we keep the F as 50. All right. So what is this equal to? 2 pi FM?
6 ohms.
6. Good. So Z1 is equal to 15 plus J6. Next step is that we write this in polar form. What is it in polar form?
$16.15549.
16 point?
15549.
At an angle of?
21 point. Oh no, this are degrees, sorry.
Good. So just put your calculator in radians and redo it. I'm happy you picked up quickly.
So 0.381.
Yes, sir.
All right, and to show that it's radians, we put a C instead of the circle for the degrees, yes? So it means that I1, the instantaneous for the fundamental, would be 120 over 16.1555 sine omega t. Now, would we have minus or plus?
Minus, sir.
So
Minus 0.381 radians. And that's it. Good. Any questions? Did I lose anybody? All right. Next. So let's see now. Kathleen. Ms. Kathleen, adjust your mic or speak loudly, shout if you must, so that we can all hear you.
I am shouting. Are you hearing me now?
All right. So what's the next thing I write, Ms. Kathleen?
So we're going to move on to the third harmonic.
Okay, so at the third harmonic.
At the third harmonic.
Or for the third harmonic, yes. What are we finding?
We're going to find the impedance. Right, sir?
Pardon?
The impedance.
I'm straining to hear you. You know.
Sir, something is wrong with my computer system.
Okay. So what are we finding?
Impedance, sir.
So Z3 is going to be equal to?
Like 20.43.
Go again?
23.43.
No, don't give me a final value yet. Just give me the complex expression.
Sir, I don't have complex.
Pardon me?
I don't have the complex
Then
expression.
how you get 23?
Sir, because I calculated it last night.
Then how did you get it?
sir, because you, okay, so because XL is 18, sir, right?
So give me the complex expression. You have the question in front of you.
Okay, so give me,
Ms. Catlin,
yes, sir.
give me the impedance in terms of the complex expression.
Okay, so it'd be 15 plus J18.
J what?
18, sir.
Okay. And in polar form, you said that was 23.43.
43.
All right, since we used 3 DPs earlier, give me 3 DPs.
23.431, I think.
At an angle of? You said you calculated it, you know. So what's the angle?
Sir, I left off that part.
0.8761.
Okay, so I3. Come, Ms. Cotton, we're burning up precious time.
Okay, so sir, I do the 20 right over the 23.43. Right, sir?
23.431 sine 3 omega t. Look at the screen, Ms. Codlin, and tell me what to write.
Okay, sir, and then it would be minus 0.76.
Thank you. All right, Burkett. So now we're comfortable with the at statements. So at the 5th harmonic, at the 5th harmonic,
So it would be at the 5th harmonic, we would have Z3.
where are you finding Z3? Oh, you're at the 5th.
Oh, Z5, sorry, sir. So it'd be Z5 would equal to.
All right, so Z5.
Z5.
Equal. Yeah, it's all right, man. I'm English.
So Z5 would be equal to 15 plus J30, which would be in polar form, which would be 33.541 at an angle of 1.107.
Okay, so I5.
I5 would be equal to, would be 15 over 33.541.
Is it that you did this already, Mr. Burkett?
No, sir, I just figured, I understand how to do the question. I understand how to do it now.
Okay.
So it's not that hard.
So you're agreeing to network easy. I look like I should have talked to you a long time.
Sir, all I can say is you know how to teach so far because I'm getting the principle.
Mr. Burkett, you mustn't try to butt up the lecture.
I know, but sir, me just know say me understand how to do it. Me not so great on the maths part, but me can understand all the principle.
Yeah, but all right. I'm just teasing. Don't take it serious. You take me serious, I'll put you in a problem. Yeah.
It's all right, sir.
All right, thank you, Mr. Burkett. All right. So we have the expression, and all we need to do is to write them out together. So the first one, I can't write over all of that. So you get I1M, whatever that 120 over, what was it? 16 is equal to sine omega t minus the 0.381. Yep. And remember, for radians, it's C plus the I2M, which is whatever that works out to be, sine 3 omega t minus 0.8761 radians plus, and so on. And that's the expression. That is what you're asked for. Any questions? Have I done anything that you're not understanding? It is at this point that you make your declarations, people. All right. So, for the next question, I just want to talk you through, time is it? 12:28. Here's a question. All right. Don't worry about that section which asks you for power factor. That is something that we'll thrash out next week, Wednesday, in our final class. I mean, I have to accept that we can't finish everything today. Now, I'm not going to do the question, but I just want to highlight a couple of things. First question. Let's see. Going down the line. So McFarlane. Not McFarlane, Martin. Kavar.
Yes, sir.
How would we determine the frequency of the waveform? So Martin,
I'm not sure, sir.
then tell me what you're not sure of, man. Because that's the only way I know how to address it. Or are we going to find the frequency?
So can I say, Spanish said the frequency equal to 1 over T.
All right, so obviously there's nothing there that gives you a T. So obviously that would not work, right? All right.
Yes, sir.
Okay, fine. So you're not sure. Miss Salmon, Tiffany, front and center.
Yes, sir.
How are we going to find the frequency?
Sir, I'm not sure, honestly.
We have all been honest, but I want to hear how you go about doing it. Being unsure is no problem. I want to hear what you do. All right. So I see Mr. Atkins' hand is up. Go ahead, Mr. Atkins.
All right, so sir. See, now we're given the omega value already in the first for the fundamental, which is 314.16, and omega is equal to 2 pi f. The transpose for it.
Thank you very much, Mr. Atkins.
And omega is equal to 2 pi f.
Yeah, man. Thank you. So, as Mr. Atkins almost correctly said, all right, we have omega, which is 314. So we can find F. All right. Now, why I said he's almost correct is that it is important that you do a quick check before you assume that the first sinusoid in the expression is the fundamental. Because I said at the start of the class that not all harmonic expressions, or not all Fourier expressions contain the fundamental. You remember me saying that? If you also look at the question we did for the full wave rectified wave, there was no fundamental. You had a DC component, and then you had the second, the fourth, and the sixth harmonics. So you need to do a quick check. And the quick check would be, in this instance, you look at 628, 942, and 1246. And if you divided each of those by 314, you would get a whole number. Can you see that? So 628 over 314 gives you 2. 942 over 314 gives you 3. 1256 over 314 gives you 4. So it is telling you that the 628, the 942, and the 1256 are the second, third, and fourth harmonics. So asking that first question, although it is simple, and you would only get 2 points for it, really, it is actually testing whether or not you understand the fundamentals. So I'm not going to come here and ask you to define harmonic or define amplitude and that sort of thing. No. We're in electrical engineering, we're in networks 1, and so it's about application. All right? So, Mr. Atkins, you understand why I said you were partially right. Right? But
yes, sir.
I still would hold 10%. All right? That said, what's the frequency, Mr. Atkinson? Atkins, sorry.
Sir.
Huh?
Sir, 1 second.
All right. So a couple of things I need to let you know. There are some basic numbers that you're going to come up against when you're dealing with once you're in engineering. These numbers must make sense to you. You all know what the value of pi is, no so? Everybody here know pi? 3.142. If I wake you up 2:30 one morning and ask you the value of pi, you all know the value. 3.142. And that's where we stop, but of course it's longer than that. But anyway, I digress. The point I'm making, that 3.142, it kind of look like the 314, no? So 3.142 times 100 gives 314.2. But if you multiply by 100, then 2f is 100. So it means that f is 50. So these things must start to become more second nature to you. An omega of 314.16 gives you a frequency of 50 hertz. All right? So let's write that down on the sticky part of your mind. Okay, amplitude. What we go about finding the amplitude? Remember, I'm not doing the question. What we go about finding the amplitude? of the third harmonic. Which is the third harmonic?
The one with 1/3, sir.
Good. So what is the amplitude?
Use the formula with EM.
No, you don't need EM. EM is not in this. So let's look at what you have.
Sir, 16 EM. No.
You deal with the formula, the expression in front of you. The one on the screen. What is the amplitude of the third harmonic? Go ahead, Mr. Miller.
Would be
what's the amplitude of that 942.48?
it would be the constant before, sir. So it would have be like 60 minus 25.
Oh, but you have no this. Well, Mr. Miller, don't let me pull it through the computer. What is it that is in front the bracket? What is in front the bracket?
You want the value that is in front.
Tell me what is in front the bracket. Talk to me, no, man. What's in front of the bracket?
You have 16.
Huh?
You have 16 minus 25.
No. Come on, gentlemen. If I was gonna multiply 16 by everything there, I would have to put a bracket here, so not say go.
There's a constant.
True. I know. So what is it that is in front of the bracket?
25/pi.
Exactly. So what is the amplitude of the third harmonic?
25/3 pi.
So easy, Mr. Miller. But you did tell me say it easy, you know, man.
Yes, sir.
But you make it look so hard now. We have to be consistent, man. If it's easy, it's easy, and we just make it easy. We don't make it more difficult than it is. So now that we have the amplitude of the third harmonic, what is the amplitude of the DC? What's the magnitude of the DC component? Mr. Miller, you know me, I go call on you, you know, so I don't know where I hide your head for. So what's the value, what's the magnitude of the DC? Just look at the screen, man. It's nothing to guess.
Magnitude of DC would have be
all right, you're going to guess. So I'm going to make a guess. Anyway, yeah, Mr. Bernard, what's the magnitude of the DC?
Sir, me believe it's 0 because you said only a DC.
Mr. Bernard, man. We have to spoil the thing, man. Look how the class are going good. Yeah, Mr. Walker. Give me the answer. Yeah.
Sir,
make sure you get the right. Yeah, Mr. Walker.
Would it be 6?
It's absolutely, it is 16. Because that is the only component that does not have a sinusoid. We said that at the beginning, you know.
Sir, but me think that for the inside of the bracket you talk about, you know, sir.
Boss man, f of t equal the whole of this. All of this is f of t. You see f of t up here, so see the equal sign there. The only thing down here that don't have any sign attached to it is 16. So the DC is 16. Right, Mr. Bernard?
Thank you, sir. Thank you for the clarification.
You're most welcome, sir. Next, I now connect it to a circuit. The circuit has a resistance at 10 ohms. So this is the circuit I'm connecting it to. All right, so this is 10 ohms. Now we don't know what C is equal to, we don't know what L is equal to, but it's not important. What we are told is that at the fundamental, note, at the fundamental, XC is 30 and XL is 5. So at the fundamental, those are the values. So what would be the impedance at, well, all right. What would be the impedance at the DC? So when the DC is acting by itself, because remember all the other questions we started at the fundamental, but at the DC component, what would be the impedance? Anybody?
10 ohms.
That's a fair guess.
I know really, I guess.
It kind of wrong though. I know. It's all right, Mr. Denham. Don't beat up yourself too hard. It's not something that is easily appreciated. But Mr. Walker looking intently on it, because he's going to give me the right answer now. So Mr. Walker, why would it not be 10?
Sir, because you have inductive and capacitive reactance, sir.
So what does that have to do with the DC? All right, you remember let's stick with you, Mr. Walker. Let's reason it together. No, man, open the mic, man. We're going to reason it. We're reasoning it about it for the benefit of the class. While Mr. Denham look outside and hopefully miss what we are saying. All right? So make a reason. Why did you say that the DC component is 16?
Sir, because it doesn't have any sign or anything connected to it. It's just by itself.
All right. So if it is not sinusoidal, what would that say about the frequency?
There is no frequency. Yeah.
So it equal what?
0.
0. Beautiful. So I'm going to continue the reasoning. So if I connect that DC to my circuit, to the circuit that we are looking at, with 0 frequency, what would Z be equal to?
Would it just be the 10 ohms, sir? Because the capacitive and inductive reactance is more.
All right. Tell me the expression for impedance for this RLC circuit. Give me the full expression in complex form.
Sir, it would be 10.
No. Don't give me numbers. No, don't give me numbers. So it's R
plus JX XL minus XC.
All right. So that is the expression for impedance. Remember in our reason, we're reasoning. So we said that at the DC, in frequency is 0. Good?
Yes, sir.
So at DC, what would R be equal to?
10, sir.
Good. What would XL be equal to?
0.
Why?
Because there's no frequency. The frequency is 0.
And therefore, XL is given by what formula?
2 pi FL.
Good. So XL is 0. But what would XC be equal to?
1 or 2 pi FC.
Which is equal to what?
0 as well, sir.
No. Remember, F is 0, you know.
Right.
So what is XC?
Would that, sir, would that mean why 1 over 0? Is that like, so that not undefined because 1 over 0 is
Absolutely. So 1 over 0 equal what?
infinity.
Infinity. So I come back to the question. What is the impedance at the DC?
Is it is it infinite? R plus?
Absolutely. So whatever R is, when we add it to infinity, we still get infinity. Agreed?
Yes, sir.
Therefore, at the DC for this circuit, because of the presence of the capacitor, the current is 0. Because the impedance at the DC would be infinitely large because of the presence of the capacitor. And that, gentlemen and ladies, is one of the applications of capacitance. It blocks DC, but it allows AC to pass. So all the capacitor will do with your DC, it just charge, and then there's no further current flow. So it blocks DC, but it allows AC to pass. Any questions? Do the rest of you understand the reasoning that Mr. Walker we're having? If you don't understand, raise your hand. No, you understand, Mr. Denham, where your error lies?
Yes, sir.
Good. And you won't make the mistake again?
Probably not.
You're a smart man. I look forward to teach you in year 4. All right? No. Now that we have dealt with the DC, oh Lord, I'm having fun and the time running out. Anyway, let's come back. Did I really say I'm having fun in a networks class? Boy, I'm really hungry. Well, let us move on. Let's move on. The values you are given, students, for the inductive and the capacitive reactances are at the fundamental. Yes? So, Mr. Harrison, what would be the capacitive reactance at the second harmonic? If at the fundamental it is 30, what would be the capacitive reactance at the second harmonic? Listen carefully. We're dealing with capacitive reactance. At the fundamental, you are told that it is 30 ohms. What would be the capacitive reactance at the second harmonic?
So it'd be 2 times that, right, sir?
Capacitive reactance. What is the relationship between capacitive reactance and frequency? What's the relationship? You drew the graph 2 weeks ago. What's the relationship between capacitive reactance and frequency? Is there a direct relationship, Mr. Harrison?
Yes, sir, but it just
you
not
see a straight line when we drew XC versus F? Did you get a straight line?
Sir, which graph are you talking about, sir? The one with the curve?
XC, capacitive reactance versus frequency. Was there a direct relationship? Or was there an inverse relationship?
The inverse relationship, sir.
Good. So if it is 30 at the fundamental, when I double the frequency, what going to happen to it? Come on, man.
That will have.
Mr. Barnett.
Yeah.
You know, see me and Mr. Harris na reason, man.
Oh, sorry.
Oh, you just come jump in our things, man. Mr. Barnett.
Go again. Go again, sir.
That's how we do it, man. Hey, Mr. Harrison, back to it. So if it is 30 and I know double the frequency, what's going to happen to the value? Since there's an inverse relationship.
Go half, sir, because the inverse of it.
Exactly. But for the inductive reactance, if it is 5 at the fundamental, what does it become at the second harmonic?
10, sir.
You see how it is, Mr. Harrison?
Yes, sir.
You see, once we start thinking about it, we realize the network's really easy. So,
yes,
this is the task for you all. You write down this question, and I'm not asking you to determine the power factor. What I want you to do is to write the complete expression for the current. So just as we have done today, we look at the DC, we look at the fundamental, then the second, then the third, then the fourth harmonic. You're going to do that and write out the complete expression for the current. And then next week, God's willing, we'll come back, we'll look at power associated with complex waves, and then we can finish that last section, which deals with power factor. All right, ladies and gentlemen. So let us see who decided to come to school today. All right. Where are we now? Attendance. Okay. Alexander.
Here, sir.
Allen, Richard Allen. All right, Atkins is here, Barnett is here. Bernard, are you here?
Yes, sir. Yes.
Bogle, yes. Campbell, Zakari. All right, this fellow case not in the class anymore. Clark, are you here? Mr. Clark not here. Let's go. Codling.
Here, sir.
Denham. Hold on, it's Bogle here?
Present, sir.
Yes, sir.
Oh, okay. Where are we? Kathleen, then Don. Ellis. No, sorry about that. Ellis. Farrell. No. Ford. Gibbs.
Here, sir.
Gordon. Halstead.
Present, sir.
Is that Halstead? Was that Halstead or Gordon? Halstead or Gordon?
Halstead, sir.
Okay. Harrison is here. Jomo Harrison. Hills.
Present, sir.
And Hemmings is here. Henry's here. Hopkins.
Present, sir.
Horn. Howell. Jackson. Johnson, Jadine. Johnson, Jonathan. Kelly.
Here, sir.
Martin is here. McIntosh, Josh David.
Here, sir.
McIntosh Lowell. Sam Miller is here. Moncrief. All right, and Mr. Maurice here. Okay. All right, let's go again. Reed is here. Richards, Dwayne Richards. Rogers. Someone is here. Samuels, Jerome Samuels. Skyers. Small, DeAndre. Marlando. Smelly. Smith, Jamil. Sterling is here. Well, hold on. Adili. Ronaldinho.
Present, sir.
Sorry about that. Rajan Stevens, Javian Taylor. Olandre Thomas. David Thompson. Vassal. Walker is here. Wallace. Walters, Karim. And finally, Garnet Williams. Garnet Williams. Wilmot. All right,
Yes,
that's
sir.
it.
Excuse me, sir.
Yes.
I don't think I heard my name.
You're not on the list, Mr. Burkett. You're an imposter. Mr. Burkett, this is your first class?
No, sir. I've been here from the first class, sir.
Oh, yes, sir.
You've even called my name for attendance multiple times. I'm just thinking you
All
missed
right,
it.
Josh Burkett.
I am here, sir.
Okay, sir. All right, that's it. Remember, come to class with the current expression for the example I just gave you. All right, and we will take it from there. Okay, have a good one.
Sir, we can ask that question, sir.
Yeah, man.
All right. Sir, you
I
said
ran
that.
out, but go on.
Yeah, I know what about. Sir, you said the capacitor block